Just a quick overview of the working principle of the algorithms that we are using. So random forest and gradient boosting, both of them are the machine. These are the tree-based learning algorithms. The main difference between both of them is that in the random forest, it goes in parallel. So you specify that how many trees are going to be generated, and then the aggregate of all the trees is the final model that depicts your prediction. While in the gradient boosting, the trees goes in sequential order. So every next tree is taking the correction factor from the previous one, and then finally, after the number you specify, you get the final output of the prediction. Neural network works in the same way that like the neuron works in the human body. So you have input layers, and there are some hidden layers that carry some generic weightage, and on the basis of that you get some output which has some error lag with the actual measured response. Then there is a correction factor that is added, and there is an update in the coefficients of the hidden layers. So this process is iterated until you get the best match response in the neural network. In the multilinear regression, there are more than one dependent variables on the basis of which you can predict your output. And in the end, the linear regression, it's just the linear regression model. You have one dependent variable on the basis of which you can predict the relation on the basis of on a line equation. So we'll discuss the results of each of the algorithm for all of the wells that we have used. That you can see that for the random forest, we have tuned the parameters. The number of the trees have been kept for the 45. So 45 trees have to be generated, randomly selecting the data in the input features, and then taking the aggregate of all those trees and giving you the prediction results. So if you see that the train and the test score is very good, while on the blind well that we have taken, the well score is not very optimum, but it's still a good match. This is showing overfitting. That indicates that we have a scarcity of data. So if we put more data into it, maybe we will be able to get a good correlation across the well here. So you are looking at just the right side of the plots. You can see the correlation of each well, the predicted response versus the actual response. So this slide is showing the results of the gradient boosting, for which we have taken the learning rate of 0.3 for the well A, 0.2 for the well B, and 1.15 for the well C. And the number of the trees has been kept randomly to get the maximum output from this algorithm. You can see the train and the test scores, and then the well score. The well score being lower than your training model shows that your model is overfitting. So this overfitting can be, as I have said earlier, that this can be avoided if you can give more data to the input.
Sir, you have 4 minutes.
Okay, sir. So next is the neural network. A neural network, you will see the similar response. You get good well score for the well A and well C, and a marginal response for the well B. This is again indicated, this is again indicating the overfitting. But if we compare this with the multilinear regression, you'll see that overall the training and the validation score of the wells, which were kept blind for this, it is consistent overall. So these are the numbers that are showing the mean absolute error and the mean squared error for the empirical relation that we have used. So this has been not used for the machine learning part. So just based on the empirical relation. So all the data have been plotted for the well A. All the models results are, you can see that there is some consistency in the data, and you will not see any outlier in this one. Statistically, as the multilinear regression is better than the next one, but still you can see that all the algorithms are within the same ranges for well A, well B, and well C. We have also done the residual analysis of the ML algorithms. So here you can see that the column for the main residual, the multilinear regression is performing better than the other. Next slide will be showing you the in this slide you can see that the residual are distributed evenly across the zero line for each well here, and data for these residuals are normally distributed. So this means that we can rely on our model. These are for the multilinear regression. So for the cross plots, we have cross plotted VP and VS. You'll see that this is the first one on the left is the recorded response, and all other are the machine learning response. You'll see the similarity for well A, well B. There is a little bit inconsistency over there, but you'll see that generally the response is similar as the recorded one, and over well C also. So we have also performed these the cross plot for the acoustic impedance versus VP-VS ratio for well A, for well B, and for well C. So you'll see that the modeled response based on the multilinear regression is best matching with the recorded response. All other algorithms are also responding to that, and the linear regression model, because of the linear assumption, it is not matching with the recorded response. We have also done the AVO modeling of the predicted shear wave. So the right one is the model response of the predicted shear wave, and the one at the left side is the actual shear wave. If you see on the intercept gradient for this 30 Hertz Ricker wavelet, the response is consistent for the predicted and the actual log response. This is for the 40 Hertz. For the more resolution part, you still see that there is a consistency between the predicted and the actual log. This was for the gas well, which is showing you on the slope intercept. You can see that the gas response. This is the other well, which is well C, which has a brine response on the reservoir, which is highlighted over here. So the predicted and the actual log response, on the basis of that, we have modeled these AVO response. Both are consistent for 30, 40, and 60 Hertz.